Hello students, welcome to PH107 Quantum Physics and Applications. Let's continue our discussion from the last lecture where we were developing the concept of statistical physics. In the last lecture, I have provided the motivation to study statistical physics, uh, which is based on the following problem that when you want to study the behavior of not one or two or few particles but large number of particles such as air molecules in a room, then we are not able to use our standard approach based on either classical mechanics where we are using Newton's equation of motion or quantum mechanical approach based on Schrodinger equation. Both the approaches becomes almost impossible to apply to understand the behavior of air molecules in a room because the number of molecules are quite large, up the order of 10 to power 23 molecules. In such scenario, we need to develop an alternate theory and less demanding theory based on the statistical physics where we cannot uh, study the properties of individual molecules, but we are interested to understand the collective behavior of the large molecules. For that, we have started looking some of the basic concepts. One of the basic concepts that we wanted to study in the last lecture is the number of particles in the energy range between E and E plus dE, which depends on the product G of E and F of E times dE, which gives the number of particles in this energy range, where G of E is your density of state, which is nothing but the number of available energy states within the energy interval E and E plus dE, and F of E is the probability of particle occupying an available energy in the interval, which is expressed in terms of the probability distribution function. And this probability distribution function also depends upon the nature of the particles, whether your particle is classical or quantum mechanical, and if it is quantum mechanical, then whether it is a boson or fermion. Okay, so this F of E depends on the particle characteristics. Okay, so the overall problem we have boiled down into finding an equilibrium configuration. So the general problem we are trying to solve is that if the total number of particles and the total energy is fixed, then what is the configuration for which this multiplicity is maximum? And in the previous lecture, I have given a simple example where I have taken the two particles in three energy levels, and these three energy levels have different degeneracy factors, and then we have asked what are the different ways in which we can distribute these two particles in three different energy states such that the total energy of the system remains constant, which was 2E. Okay, and then we have seen that this multiplicity, let's say the configuration changes, and there are some less probable and most probable configuration, depends on what kind of particles we are talking about. So now we are trying to understand how to estimate or how to calculate the multiplicity, the configuration for which this multiplicity is maximum, and let's see how we can calculate it. So let's try to again come up with a simple example. So here is simple example, and then we are going to make it easy, not make it difficult. So let's start by assuming that you have a two state, so I is equal to 2, and then you have the degeneracy factor 1 for both the states, and n is the total number of particles. Okay, so we are considering a system with two non-degenerate energy states E1 and E2 because I is equal to 2, in which n particles has to be distributed such that the total number of particles and total energy remains constant. Okay, so this problem is similar to distributing n numbered billiard balls. Now we are talking about the classical particle, so we can put a labeling on the particle. So this problem is analogous to distributing n numbered billiard ball in two numbered containers. Okay, so here is you have two containers, so you could think this is a representative of two energy levels, and these are your n numbered balls, and now you want to put these balls into these two containers. So let's ask the first very simple question to estimate this Q value. So what is the possibilities, or what are the ways in which you don't want to put any balls in this first container? So n1 is equal to 0, and all the balls, all the billiards ball into the second container. There is only one way of putting no ball in container 1 and all the balls in container 2. Okay, now let's increase the sophistication or the complexity of the problem. Now let's ask, if you want to put one ball into the container 1 and rest of the n minus 1 ball into the container 2, so what are the ways? Okay, so there is only n ways. There are n ways of putting one ball into the container 1 and rest of the n minus 1 balls in container 2. So there are n ways. Okay, now let's increase it. Now you want to put two balls into the first container and n minus 2 balls into the second container. So how many ways are this is possible? So this is possible by n times n minus 1 by factorial 2. So this is the standard answer which is possible for this possibility, and which you have seen in your earlier classes also. So if you want to put the two balls in container 1 and rest of the n minus 2 balls into the container 2, so how many ways are possible? So these are possible by n2. Okay, now which is n minus 1 by factorial 2, and there are n choices for the first ball in the first container, and for each of them n minus 1 choices for the second ball in the first container. So here we have shown that. Now let's say you have put alpha and beta ball into the container 1 and rest of the n minus 2 balls into the container 2. What we are also considering in this particular situation, that we do not want to count when you have alpha beta or beta alpha as two different cases. So we divide by factorial 2. Okay, now let's increase the complexity one more step. So what are the possible ways by which you put 3 balls in container 1 and n minus 3 balls in container 2? So you know this is the standard answer. Now you can guess that this will be n minus 1 times n minus 2 divided by factorial 3. So this is what n factorial n divided by factorial 3 times n minus 3 factorial. Okay, so now let's make it more general. So what are the possible ways when you put n1 balls in container 1 and rest of the n minus n1 ball into the container 2? So it will be n1 factorial divided by n minus 1 factorial times n minus 1 factorial. So if you simplify this thing which I have said just now, then you will see that this will be nothing but it will be simplified as n factorial divided by n1 factorial n2 factorial. Okay, so now what we could do, we can extend this concept furthermore, and we say that okay, let's make two partitions of the second container. Okay, and then ask what are the possible ways by putting this ball and how the problem or how the answer changes. Now we want to make sure that your n2 remains the sum of the nu1 and nu2. So these are the two containers which are represented by nu1 and nu2. So now you ask the number of ways of realizing the configuration nu1 nu2 within the sub compartment of the second container, and you know the answer. So this will be again n2 factorial divided by nu1 factorial times nu2 factorial, and this is the same logic that we have used in the previous one. So let me go back here. So what we have done, we have n1 here and we have n minus n1 which is equivalent to your n2, and then the answer was your n factorial divided by n1 factorial n2 factorial. So you think of that you have a total n and this total n is divided into two pieces, n1 and n2, such that n1 plus n2 is equal to n, and then the answer is this one. So the same goes here. So now your n2 is divided into nu1 and nu2 in such a way that nu1 plus nu2 remains n2, and now you are asking what are the number of ways of realizing the configuration nu1 nu2 within this sum compartment of second container, and the answer will be n2 factorial divided by nu1 factorial times nu2 factorial. So now we can use this result and ask the question for the total system, which composed of first container times second and third subcontainers. So we could consider this as a three containers as n1 times nu1 nu2 balls, such that your probability of this q of n1 nu1 nu2 becomes, so this is the one that comes out from the first treatment, and this is from the second treatment, and you see that now nu2 factorial and nu2 factorial get cancel it out, and now you have left with n factorial divided by n1 factorial times nu1 factorial nu2 factorial. So you see that the total n is divided into three subpieces, n1, nu1 and nu2, such that n1 plus nu1 plus nu2 is equal to n, and now we can relabel these nu1 nu2 by n2 n3 by some relabeling. Then we can say that if you are asking q times n1 into n3, this will be n1 factorial divided by n1 factorial, n2 factorial, n3 factorial, and now you can extend it to not only to the 3 but into the n. So then you can ask a q of ni is equal to n factorial divided by product of ni factorials, where the product of I. Okay, so now we have not considered any kind of degeneracy of any energy states. So each energy states have no degeneracy, or you can say the gi is equal to 1 for each energy states. Okay, so now if we want to consider the degeneracy in our problem, and let's ask the following question. So if we consider the state I with energy ei to be gi fold degenerate, okay, then we need to consider a group of gi containers with identical energy ei with all the labor I to distribute the ni billiards ball. What it means that ni balls can be distributed in gi copies. So what you have done, you have a similar container ni gi times, and then you want to distribute these ni balls. So ni balls can be distributed in gi copies of the container labeled I in gi power ni possible ways. The first of the ni balls can be placed in any of the gi container, so can be the second, third, fourth, and so on. Same holds true for distribution of nj balls into the gj copies of the container labeled gj. So the total q of ni, where each state has a gi fold degeneracy, then this is the one that we have obtained from the first argument, and this is the second part which we have obtained due to the degeneracy factor. Okay, so now our job is to optimize this quantity, which is the q of ni, and we want to optimize this quantity to obtain the stable or equilibrium configuration. Okay, now when we want to optimize this expression, we have to also make sure that we are treating, or we are imposing, these two constraints, that the total number of particles and the total energy of the system remains constant. Okay, and this optimization is done using a mathematical technique known as Lagrange multiplier, so which we are going to use it in this our problem. Okay, so once we will use the notion of Lagrange multipliers and we'll try to optimize q of ni with these two constraints, this will give the condition for q of ni to be maximized with this expression, where ni over gi is equal to e times alpha times e to the power alpha times e to the power minus beta ei, where alpha and beta are two constant which we will determine. Okay, how you will go from this expression to optimize this maximum what you say the stable or equilibrium configuration with these two constants using a Lagrange multiplier. The detailed derivation will be provided in a separate handwritten notes to you. Okay, so now we will see in a moment that this constant beta will turn out to be 1 over kb times t. So let's substitute for the time being this one, and I have taken gi here. So I have written my ni is equal to gi times e to the power alpha times e to the power minus ei over kbt, where 1 over kbt is your beta. Okay, and this equation represent the Maxwell-Boltzmann distribution function, which I am going to write as f of mb, because f was your probability distribution function. So here we are treating particles as classical particles and distinguishable particles. So that's why we have to use Maxwell-Boltzmann distribution. So here is the subscript mb, and here is for ith state. So this is ei. Okay, so this is your Maxwell-Boltzmann distribution function, and let's see what we can learn more about it. So here are one constant, total number of particles is constant. So let's substitute the expression of ni from the previous slide, which was your gi times e to the power alpha times e to the power minus beta ei. This comes out to be the same, and now this e to the power alpha is your I independent, so I can take it outside from this summation. So now I can rewrite this e to the power alpha as n divided by summation over I gi times e to the power minus beta ei. Okay, now I have obtained the expression for my e to the power alpha. I can substitute this expression of e to the power alpha back to the expression of ni. So you see that this is my expression of ni becomes, where ni becomes n times gi e to the power minus beta ei, and this terms comes because of the e to the power alpha 1 over summation over I gi e to the power minus beta ei, this one. Okay, now I can define probability of finding the particle in state I. So you know how to define the probability in this case. This probability is defined as pi is equal to ni divided by n. I know the expression of ni, so if I use this expression of ni, n will be cancel it out, and this will be my probability of finding the particle in state I. Okay, now once I have a probability, and if you recall our previous lectures where we were discussing about the probability distribution and different kind of average values or the mean values, then once we know the probability of finding the particle in state I, then we can estimate the mean energy as E bar is equal to Pi, which is the probability distribution function, times Ei, and we have to sum over I. So once we use this expression, then we can write down the mean energy for the classical particle is in this following fashion, where this expression 1 over gi times e to the power minus beta ei is written as 1 over z, and this z is nothing but is the partition function. Okay, so now this is your small exercise that you can verify that your average energy or the mean energy can be written as minus partial derivative of ln z with respect to the beta. So this you can verify, where z is your partition function and beta is your this constant here, which is 1 over kbt. Okay, now if you want to compute the average value of any other variable, for example y, then what you need to do that you have to multiply this probability pi times this value yi, and then you have to sum over all possible I, and this will give you the average value of any parameter y. Okay, so let's write down the expression of e to the power alpha as a. Then we can write down the total number of particles n as summation over ni, and you remember that your ni was your gi times e to the power alpha, which I am going to rewrite as a times e to the power minus ei over kbt. And now we want to go from a discrete summation to the continuous limit, and we have seen that in such situations we have to replace your summation by integration. So the summation of Ni will be replaced over integration over of d of n over e, and if you substitute this d of Ne, remember from our recap slides, this d of n is nothing but g of e, which is the density of state, times f of mb, which is the probability distribution function, times de, and we know that this probability distribution function is nothing but a times e to the power minus e over kbt. So now I can express my a as, if you substitute this expression here, then I can rewrite my a as e to the power alpha is nothing but n divided by ge times e to the power minus e over kBT times dE. And remember, this density of a state is also a function of energy, so it cannot be taken outside of this integral. Okay, now let's come with the idea that let's have a point particles of an ideal gases, and these are the ideal gases which are made of mono atomic systems. So the energy of point particles of an ideal gas is purely translational kinetic energy. What it means that the energy of each molecule is of the form of half mv square. So this is your total energy of your point particles of an ideal gas, and if you use this total energy and you know that this speed of the gas particles vary continuously from 0 to infinite, then it means that your energy also goes from 0 to infinite continuously, and in such situation the Maxwell-Boltzmann distribution can be written as d of Ne is equal to Ne times dE, which is Ge times A, which we have seen in the previous slide, and then I have just substituted the value of energy as half mv square, so it will be e to the power minus half mv square divided by kBT times dt. Okay, so before we go to the next topic, let's ask a following question. This you need to answer: what is Lagrange multipliers and why it is needed? Okay, now let's move to the quantum distribution function. We have seen the distribution function for a classical particle, which is nothing but a Maxwell-Boltzmann distribution function, and which has this exponential form. Now we have to go to the quantum particles, and first we have to recall ourselves what are the quantum particles. Okay, so we have to first talk about the fermions, and we have to compute the Q of Ni for fermions. So if the particles becomes indistinguishable, they are called quantum particles, and it means that the numbering of the billiards ball is gone. This we have seen in the previous lecture also, that the red and blue colors which we are using for the classical particles had gone, and we have used all the particles labeled as blue. So in this case also your particles become indistinguishable, so you do not have any more numberings of your billiards ball. Moreover, we are discussing about the fermions. It means that we have to put another restriction, which is coming from the Pauli exclusion principle, that that the restriction of occupancy of each state by one particle. So each state is occupied by one particle. Okay. In this case, that unlike the distinguishable particles where your Q of Ni was n factorial divided by a product of Ni, here your Q of Ni will become 1, because there is only one way that you can distribute these indistinguishable n particles in each state obeying the Pauli exclusion principle. So this is your Q of Ni for a fermion. However, still we have not considered any degeneracy of your energy state. So once we consider the degeneracy, so here is again this table you have seen in the previous lecture also, that if each state has different degeneracy factors. So let's say the ith state with energy Ei has a Gi-fold degeneracy, and this can have Ni1, then we have to keep in mind that there is a further restrictions of the occupancy of each state by only one particles. In such situation, we have to ask how to fill Gi states of energy Ei with Ni fermions, and you know the answer. Okay, it is nothing but it's a Gi Ni, and then it is Gi factorial divided by Ni factorial times gi minus ni factorial. So this is what we have obtained due to the degeneracy factor. Now once we substitute all these values to obtain the q of ni, so you see that there was nothing one, and this is the total factor that is originating due to the degeneracy. If you compare this expression with the classical particles, then you have seen that here we have this additional factor, and this was coming because our particles were distinguishable. And if you want to label or want to compare these two expressions into the equal footing, then you have to put 1 here. So I have put 1 here, which is equivalent to this quantity, and this degeneracy factor in the case of quantum particles is replaced by this one. So this is your q of ni. And now, as we have seen in the earlier slides, that now we need to optimize this q of ni with two constraint, that the total number of particles and the total energy of the system is constant, and we can do it. Okay, so once you follow this thing, and the detailed derivation of this step from this step to this step is again is going to be provided by the handwritten notes to you. So then you will obtain that ni over gi is equal to 1 over 1 plus e to the power minus alpha plus beta ei, where alpha and beta are the two constants. Okay, and now I can rewrite this e to the power minus alpha is equal to a, and you know that beta is 1 over kbt times. Then I can write my ni is equal to gi over 1 plus a e to the power ei divided by kbt. Okay, so now we can evaluate the expression of a or e to the power minus alpha, as we have done in the case of the classical particles, by using these conditions. And once you use this condition, then we can obtain what will come out for the alpha. Okay, and now because we are talking about the fermion, so here we are going to introduce something is called Fermi energy times this beta. So your e to the power minus alpha comes out to be e to the power minus ef divided by kbt, where ef is your Fermi energy. Okay, so in the term in the language of Fermi energy, your ni is written as gi divided by 1 plus e to the power ei times ef divided by kbt. Okay, and now we can use again the continuum limit, where your summation of ni is replaced by integration over d of ne, and now we can write the expression of d of ne as g of e times this Fermi-Dirac distribution function times dE, and we know what is the expression for the Fermi-Dirac distribution in this case, and this is the expression for the Fermi-Dirac distribution that governs the equilibrium behavior of your fermions or electrons. Okay, now you can plot this Fermi-Dirac distribution for two different temperatures, and you can see that this x-axis is your energy and the y-axis is your distribution function. And you can see that when your temperature is 0 at t is equal to 0 Kelvin, you have a step-like function that all the states up to the Fermi energies are occupied with the probability, and as you increase the temperature, your distribution function changes from function or sharp drop to a smooth change, and this difference from here to here is equivalent to the 2 kbt. Okay, and this is the Fermi-Dirac distribution function expression that we have seen in the previous slides. Okay, now let's go and ask the question for the Bose-Einstein distribution, or the Q of any for the bosons. These are also quantum particles, so these are the indistinguishable particles. Okay, however, there is no Pauli exclusion principle for the bosons. So bosons are indistinguishable, but the restriction of occupancy of each state by only one particle is gone. So a state I may be occupied by any number of particles. Okay, so here what I have here is my different of g of I, and here I want to distribute ni particles in the state of energy ei with the degeneracy factor g of I. So I can ask, how many ways can we arrange ni identical balls and gi minus 1 partition, which will is your representative of your degeneracy? And the answer is simple. So we can write down ni plus gi minus 1 and gi minus 1. So the answer will be your ni plus gi minus 1 factorial divided by ni factorial times gi minus 1 factorial. So this is my let's say the q of ni, and this is your one for the indistinguishable particle what we have seen, and this factor comes because of the degeneracy of your state for the case of bosons, where each state can be occupied by the any number of particles. So this is the factor that comes out. And now if you like to optimize this q of ni to obtain the equilibrium configuration with two constraints, then we will obtain this expression. And as I said that once you have done the two derivation or you have seen the handwritten note, then you can easily get this expression also, where ni divided by gi is equal to 1 divided by e to the power minus alpha plus beta ei minus 1. And now you can obtain the expression for e to the power minus alpha as we have done in the two earlier cases, and we can use this continuum limit, and here my distribution function will be my Bose-Einstein distribution function. And once you do everything careful, then you can see that now e to the power minus alpha is written as a, and this is your Bose-Einstein distribution function which governs the behavior of bosons. Okay, so this is your Bose-Einstein distribution function, and we can obtain, as I said, that the value of this by using the same constant. And if you use this constant or in the continuum limit, where we can rearrange these terms in a different way. Okay, so once you use this, you can do it by yourself. Then this Bose-Einstein distribution function is written in a simplified way as 1 over e to the power e divided by kbt minus 1. Okay, and this is also known as the Planckian equilibrium distribution function. Okay, so now what I can do, I can try to plot the three distribution functions as a function of energy, and here what I have plotted along the y-axis is the probability that energy state EI is occupied. We have seen that at some finite temperature your Fermi-Dirac distribution function is more like a step function, and there is some smoothing out here, and this is at EF is equal to 2 EB. Okay, and then you have a Maxwell distribution function which is exponentially decreasing function, and this is your Bose-Einstein condensation, that if you go to the smaller and smaller energy, all the particles is going to be occupied, so this goes to 1. But interesting thing is that as you go to the higher and higher energy, okay, then what will happen, that all the three distribution functions start merging to the classical distribution function. It means that if the temperature are higher and higher, then all the particles are going to behave like a classical particle. So we will discuss this case furthermore, and now in the next class we are going to obtain the expression for the density of states for the classical particles, and we will see for the quantum particles also. So note down, this result is shown for a temperature at 5000 Kelvin. Okay, now before I end this lecture, let me provide the recommended reading. So again, you can go back to the chapter 10 of modern physics by Survey and co-authors and read the chapter 10 statistical physics. Thank you very much, and see you in the next class.